So we've been spending time looking at motion, trying to understand motion, and now we're going to move on to trying to not only being able to describe motion, but maybe to try to understand a little bit more about why the motions occur in the first place. And so this is going to be our discussion, the beginning of our discussion of Newton's three laws, which will be a big undercurrent of the whole course. So again, just a recap of where we are. We've described motion, position, velocity, acceleration. We have some equations to look at a very special kind of motion, which is constant acceleration, and we can describe that in one dimension or two dimensions. And so now we're going to move on and look at the rules from Isaac Newton, his three laws. So these were published in the Principia Mathematica in 1687. And these are the three laws of motion. And I've talked about this a little bit before, but again, it's good to stop and just think about this. You know, for a very long time, people weren't able to put these together. So that tells you a couple things. First of all, these are pretty important laws. And number two, they're also not very, I would say, intuitive. I mean, I think once you learn them, once you get used to them, you can kind of look back and say, oh, these are maybe obvious or something like that, but in reality that's not true. I mean, many very smart people lived and were not able to come up with these. So just think about that if you find yourself struggling in trying to interpret these and use these. So these laws describe a great deal of the motion we see in our everyday lives. Almost everything that we can experience you can describe with Newton's laws. A couple of exceptions are very, very small. Okay, like the physics of electrons and such, that would be quantum mechanics, and also things moving very, very fast, the physics of objects moving close to the speed of light, which you would need Einstein's special relativity to understand more about. So these laws are going to give well-defined meaning to terms. A couple of these terms would be force and mass. And what we're looking at now is the study of what's called dynamics, which you can describe or define as why things move. So a force is a push or a pull on an object, and we're going to spend a lot of time starting out trying to understand forces, trying to figure out what's causing forces, because I think that can be really tricky, especially when you're new to this. There'll be two types of forces. There's a contact force, okay, and that's where there's basically whatever's applying the force is actually contacting the object in question. So what we'll typically do with these problems is we'll have some object, and we're trying to learn more about its motion, its dynamics, and we'll try to figure out what forces are acting on it. And a contact force is something that has to be touching it. So like I push on the desk or a rope holding up a picture. There's also non-contact forces, which apply, which you could call an action at a distance. Okay, so there's a number of these. Gravity, also the force due to electric fields and magnetic fields. The good news is for us, in this quarter, okay, it's possible that maybe a homework problem might bring up something else, but in general, the only non-contact force we'll deal with is gravity. Okay, and so that is helpful because one of the big problems we'll deal with is, what are the forces acting on this object? And with the exception of gravity, which the object that applies that force would be some other mass. With the exception of gravity, the object applying a force has to be in contact with our object. And so that will hopefully prove helpful. And so let's look at this question here. So a hand pushes a physics textbook across a rough table with a constant velocity. How many objects apply a force on the book? So think about this for a second and we'll talk about it. Okay. Hopefully you got three objects. So the three objects that would be applying a force on this book would be that person's hand. So the hand is in contact the whole time. The second object would be the table. So the table is pushing up on the object. It's also applying a frictional force, which is, this word rough. That's how physics textbooks like to make you aware that friction is there. And finally, the third object that's applying a force on this book would be the Earth. Okay, so it's applying a gravitational force. And so these two would be the contact forces, and this one would be the one non-contact force. Now let's look at another situation. So this is similar, okay, except in this case, a hand gives a physics textbook a quick push across a rough table, giving it initial velocity, and then it lets go. So how many objects apply a force on the book as it slides across the table? So go ahead and think about this one, and we'll talk about that. All right. So hopefully you got 2. And so here I made a little typo. This should be then letting go. But so in this one here, when the book is sliding across the table, so if you look at those 3 forces from before, the hand is no longer there. The hand, okay, gives it its initial push, okay, so you can think about it as being responsible in some way for the motion. But as it's sliding across that table, okay, so as it slides across the table, the only forces acting would be the table, right, which is pressing up and applying a frictional force. So I'll call that the table, and then the earth. And so like I said, we're sort of starting out now, but a lot of what will give us troubles will be just determining what are the things that are applying a force on our objects. So Newton's first law is stated like this: an object continues in its initial state of rest or motion with constant velocity unless it is acted upon by an unbalanced or net external force. And so there's a lot to unpack here, and so we'll spend some time doing that. But a nice sort of simple way to think about it is if there is no net force, and by net force you mean like overall force or unbalanced force, then there is no acceleration, right? And so we know that acceleration is something that changes our velocity, right? And so his first rule can be stated this way too: if there is no net force, there is no acceleration. And this is, I think, at least, easy to miss, since much of what we experience in our everyday life seems to violate this law. And so I think this is sort of if you had to put a finger on why this was so difficult for human beings to figure out, I think this is the reason, right? There are lots of cases where, at least on the surface, right, this law seems to be violated. But when you dig deep and unpack it, you can really see, where the issues come from. And so some of these come from very subtle forces like friction and gravity, which of course we're going to spend lots of time discussing. So let's look at a conceptual problem. In general, what will happen to an object's velocity if there is no net force acting on it? So take a second and think about this, and then we'll talk about it. Okay, so hopefully you thought about this and got an answer along the lines of that it'll stay the same. So if the velocity is 0, it'll stay at rest. If the velocity is some non-zero value, it will remain that value. And so this is a tricky thing to kind of think about, this idea, but that's what's buried in this law, is that basically if there is no net force acting on an object, its velocity will remain the same. And its velocity can either be 0 or some non-zero value. And in both cases, it'll have to do that. So let's try another conceptual problem. If an object has no acceleration, can you conclude that there are no forces acting on it? So think about this one, and we'll talk about it in a second. All right, so there may be forces acting on it. However, there is no net force acting on it. And what that means is, there may be some forces acting on it, but those forces are canceling out. Okay, so like a really sort of bare example would be if you put a box on a table like this. Okay, what there's going to be is there's going to be a force up from the table, so we'll call it force. We usually call this the normal force up, and then there'll be the force due to gravity from the earth of F of G. We should probably just call that F of G for force of gravity. And what happens in most cases is these two forces balance out. And so on this box there is no net force, and so there is no acceleration on this box. But of course there are forces acting on it. So these are kind of some things that can be a little bit tricky about this first law. And finally, another one, conceptual problem number 3. You are watching an old episode of your favorite science fiction television show when you see the following scene. A starship is shown cruising through space with a constant velocity. Its engines turned on full blast. As the starship nears the space station it wants to visit, the captain turns the engines off and the ship is shown gliding to a stop. Looking at this through the eyes of a physicist, briefly explain what things are wrong with this scene. So again, think about this one, and then we'll talk about it. All right, and so the big thing here is that in space there is no friction, right? And so when the rockets ended, right, basically the ship had some velocity, and as long as they're in sort of deep space and there's nothing else there, there's going to be no forces on them, and so there's nothing to stop that velocity, right? Now on Earth, right, and stuff that we see every day, there's typically a frictional force somewhere that will sort of slow the things down, right? Like if you take your car and you're driving, you take your foot off the accelerator, generally your car will come to a stop, but this is due to friction. And so there is none of this in space. Okay. So Newton's second law, which is related, an unbalanced force on an object results in an acceleration, where the acceleration is found by this equation. And so this is probably something you've seen before. So I'm going to call it, start out, the force net. The net force is going to be equal to the mass times the acceleration. And the acceleration A of an object is proportional to the net force, F net, acting on it, and inversely proportional to what we call the mass of the object. This is Newton's second law. And what I'll typically do a lot of times is write it this way. Now, it's really important that we should say that these are vector quantities. And we'll see where that becomes important as we move on. But again, what this says here, it's the sum of the forces. And so you can look at this and say, well, let's just suppose that all the forces add up to 0 on some object that has a mass. Well, that will imply that the acceleration is 0, which implies that the velocity won't change, which is entirely consistent with the first law. So net force, so again, a force has a magnitude and direction. Adding forces is like adding vectors, and so this is definitely a part where our knowledge of using vectors will come in really handy. And so the net force is just the sum of all the forces acting on an object. And so, like, for instance, maybe there's a box here, and I'm pushing on it with a force of 20 pounds, and then pushing that way with a force of 20 pounds. So this is a case where those two forces would cancel, so there would be no net force, right? But then, of course, if I was to say then someone else came and pushed with 10 pounds that way, then there would be an unbalanced force. And so, of course, you've got to account for all the different forces when you're looking at problems such as these. The units of force. So force is, again, this is vector quantity, but if you just look at the sort of absolute values here, then the force is going to be units of newtons, and the units there will be kilogram meters per second squared. And let's try one more clicker question. So here's a block. Assume the block below is pulled by some force. We'll call it force of pull, and that there is a force of friction that works on the block in the opposite direction. We're assuming that at the moment we're looking at, the block moves at a constant velocity to the right, which must be true. And note arrows of the two forces are not drawn to scale. So think about this one, and we'll talk about it. All right, so this one here is going to be, B. So the two forces are going to be equal. And how do we get this? Well, basically, in this case here, it's moving at constant velocity, right, which tells us that there can't be any acceleration. And so one way to sort of think about this would be sort of say that the sum of the forces equals m times a. And let's just sort of say that we're making this the x direction going that way. And so this would technically be the force in the x direction and the acceleration in the x direction. Well, we know that that's 0 because there is no acceleration. And so that means the total forces have to equal 0. And so in one sense, what I could do is I could say, well, the total forces would be the positive force of the pull minus the force of the friction equals to 0, which hopefully you can see implies that those two forces must be equal. All right. Now, the thing is that at some point in the past of this problem, there must have been a net force to get this thing moving with the velocity in the first place. But at this particular moment, these two forces are canceling out. And that, I think that can be pretty tricky to kind of get your head around. And so just real quick, so what we're going to do a lot with this particular material is, again, so we have F equals ma. It's a vector equation, so you can think about these as being vectors. And what that means for us is oftentimes we'll be working in situations that are two-dimensional, and so we'll have two versions of this, the version in the x direction and the version in the y direction. And so what will happen is what you can imagine one possibility would be is we'll be given some sort of object. Our job is to find the forces acting on the object, find those accelerations, and then once we find those accelerations, if we wanted to, what will happen often is the problem you're looking at will then have you determine, okay, how far does the object go in 30 seconds, or something like that, basically using these equations that we've been using up until now. All right, and so we'll move on and start doing that.